Let's keep looking RM signal. This is part B. In part A, we defined the RM signal, what it looks like in discrete domain, in continuous domain, and what is really physical meaning in terms of electronics. This time, let's um, look at this application notes from Keysight. It's a really good one. It's make better AC RMS measurements with a digital multimeter. And so the introduction part basically talk about the, we talk about this in the first part. It's about definition RMS, how to do that. And in terms of signals for a sine wave, common voltage parameters, we can define average signals, RM signals, peak to peak signals, and peak to peak. Okay, and remember the average is different from our RMS. RMS is more popular. We later will talk about how do we convert from RMS to peak in general. Okay, what's really interesting here is how your digital multimeter measure RMS. And the first method is very straightforward. Basically, you can just measure the thermal power. You pass the signal to the multimeter. Basically, the circuitry, you pass the AC signals. You can pass a resistive load, and this resistive load will generate heat. Then you have other circuits to measure how much heat you generate. So this is that way you can convert any signals into RMS. That's basically the definition of the RMS signals. And so the signal cost can measure any AC wave types, really not depend on shape the AC input. And another one is uses here is called peak and averaging AC to DC converters. This is basically used in most very handheld multimeters or the cheap multimeters. The assumption here is assume your signals always have a sine wave. Because if you have a sine wave, if we know the peak value or we know the average value, we could just use the equation. It's very simple with a factor, and we could turn that signal into RMS. Clearly, this is very limited applications. If your signal have harmonics, or if your signal is not a pure sine wave, like a triangular wave or some other shapes, it will cause a lot of errors in the measurements. So it's definitely not the best option, but it's a very cheap, practical options. And the most time people use this for to measure light power is pretty much very similar to a pure AC signal. And another way is to use analog AC to DC converters. And eventually, if we remember the RMS signals, we basically just, just some mathematic manipulation. So, and you can explore use op amps or use to explore the nonlinearity properties with transistors or some diode. For example, you can do the multiplication here, like a squared. You can use a capacitor to do the averaging and use a nonlinearity with the transistor to do the square roots. So then you can purely use analog devices to calculate the RMS. Another way to do is use digital sampling. This is most true RMS multimeters try to use this method. So what's so-called true RMS signals or true RMS digital multimeters? That basically means you not rely on the assumption of the signal is a sine wave. You measure the peak value or average value to calculate RMS. You actually sample the whole wave like this. Then once you have the data points, you can calculate the RMS value in the DSP, digital logic. And of course, the assumption here is you have to assume this signal is a periodical signal. The signal will keep repeat itself. And to improve the measurement resolutions, you also can sample different periods with a little bit of offset. Equivalent, you have more samples than that. So this is a kind of a compromise between the price and the implementation. So you can use this way to measure both not only sine wave, but also you can measure triangular wave for example. So this is very popular. And here we talk about how the signal affects the quality of your measurements and what happens if your signal is a triangular wave or different shape, and you're gonna have a just remember this crest factor, the definition. That was a very important parameters to characterize the wave. So the RMS low, for example, low duty cycle pulse train, it will be very difficult to measure in here. So you can just keep looking at this. Let's keep looking. Avoid common measurement traps. And measurement scales. Of course, you need to pay attention to that. What I'm really interested in this part is the AC/DC coupling. What we talk about here, we're normally you have a wave, say, we assume this wave is random wave like this. It's AC coupled wave. That means in terms of time scale, this voltage signals go both above go to the positive side, also go to the next side, positive side next time. The mean, the average over certain time lengths will be 0. But in reality, most signal probably will look like something like this. Very similar to that, but you have a DC offset. Okay, so here's your 0 volts axis here, but you have a certain DC offset. Okay, how do you measure this wave? This could be tricky to what's the RMS value of this wave could be very tricky to measure, but it's good points. We have this. We can use this formula. Basically, what that means, the RMS a wave, a AC wave with a DC offsets. The RMS basically equals. You can use measure RMS value of the AC wave and square that. There's these two should not be here, and also the square the DC offset, then add them together, take the square root to that. Basically, you can calculate the two parts and square them and then take square roots. Okay, so let's just quickly prove this, why we can do this. Okay, let's say VRMS squared, we just take the square root so we can remove square root. By definition, you have 1 over t, 0 over t, and v squared dt. Okay, if we have a if this is v, have a vd, the DC offset, plus a va, the AC signal, squared dt. And what we have here, we can expand this squared here. So we have vd squared times 2vd va plus va squared and dt. Okay, and then you can separate this integration into 3 parts. And the first part, I put bracket here. First part is vd squared dt, and the second part is 0t 2vd va and plus 0 to t va squared dt here too. Okay, and so this is from 0 to t, vd squared dt, basically the constant. What we get is 1 over t, this part, just take the vd square out, then the 0 to t, integrate t will be a capital T. And this part, we can take the vd out, this is 2vd out, because it's a constant, DC offset, then the integral is 0 to t, va dt. Then this part, 0 to t, va squared dt. Okay, and what we have here, first we can look at this part, the va dt 0t. Basically, this is the AC signal, AC coupled signal, the area of the AC coupled signal. Okay, we know the AC coupled signal areas in average will cancel out, so it will be this will be 0. And what we left over here is vd squared times t. If we get 1 over t inside that, we just get vd squared. And here, 1 over t and 0t, and VA squared dt. Okay, so we have VD squared, and this is basically the RMS value will be the AC parts, so it's VA RMS squared. In other words, so we can measure the DC part first, and we can get the DC value first, then use the AC coupled RMS measurements, then measure the RMS for the AC part, then we can combine them together with this equation. This will be very useful in practical. And we also talk about bandwidth error, self-heating error, settling time, or other stuff. But it's, you can look at this documentation for details, and hopefully this will give you more insight about RMS value and how to measure RMS value.